it's Amy, and today we'll be going over Digital Ding Dong Ditch. When I found out my best friend Matt has a wireless doorbell, I decided to hack it. Essentially what I did was I took an RTL-SDR, or $14 software-defined radio, used it to sniff the radio frequency or signal of his doorbell, reverse engineered it, and then created this device using an Arduino, an RF transmitter, and a GSM board to replay the signal to ring his doorbell. So anywhere in the world I am, I can send a text message to this device and it will ring his doorbell. So first let's see it in action, and then I'll thoroughly go step by step of this entire process. So you can also learn how to reverse engineer a similar signal or any other kind of radio signal, and also how to create and code a device like this. So while I started testing this, my friend Liana came out and helped by covertly recording Matt while I would send SMSs from home and trigger his doorbell to ring. But now that the jig is up, I just learned that while I was doing this, because of all the ringing in the house, Matt's wife came out and removed the doorbell button from the wall so that no one could press it. So now he's coming outside and he's like, how is this thing ringing? We don't even have a doorbell anymore, and it keeps on ringing. This makes no sense. I can just imagine wondering what's going on. It wasn't long before he texted me asking if I was the culprit. Now, let's go over the first part, which is reverse engineering or hacking radio frequencies. We're going to use this awesome device. It's inexpensive, it's about $14 on Amazon. This is called RTL-SDR. RTL, which this really annoys me, somehow stands for Realtek, even though I think that should be RLT. But it's RTL, and SDR is software-defined radio. It allows you to use a simple hardware device like this to pick up radio frequencies, and then it sends those raw samples or raw IQ samples into your computer, at which point you use software to actually interpret or demodulate the data. Let's quickly go over what we're looking at here with this GQRX. And there's other software you can use. If you're on Windows, you can use something called SDR Sharp. You can actually use that on Mac by using software called Mono to compile SDR Sharp. There's also console applications you can use to listen in, and we'll actually be using something called RTL-FM to demodulate a signal in a bit. You can probably do that in this software, but I prefer it from the command line. It's just it's quicker that way. So what we're looking at here is we have our GQRX window. We have the frequency up here. This is essentially the frequency we're listening to. We're listening to 403 megahertz. Down here you can see this graph, or this is an FFT plot, and what we're seeing is we're seeing from frequency 403.151 megahertz all the way to 404.5 megahertz. Up here we have amplitude, so we are pretty much, and we can bring that down because we can basically bring this down here and create what's called a noise floor, because we don't actually care about the signal unless we see something up, right? So there's some sort of signal here around 403.1, and we can more easily see that here. Let's bring that up a little bit. Cool. Now what this down here is a waterfall display. So this is over time recording, or it's essentially a snapshot over time of this FFT display. Now what are these frequencies? If you're familiar with, let's say, FM radio, we can go down into around 100 megahertz. Alright, so there's clearly a strong signal around 102.3. So this is 102.3 megahertz. So if you were to tune your radio, your FM radio to 102.3, then we should actually be able to hear some station. Now what's cool is that GQRX has modulation or demodulation built in. So we can actually say this should be like wideband FM mono radio. And let's see if we can hear that. Yeah. My jam, and we can basically tune with this guy right here. So that's pretty cool. So we're actually listening to FM radio off this device just because we tuned into an FM station and demodulated as FM. If we tried to listen to it as AM, it would sound wrong. So what we're going to do is first figure out what frequency Matt's doorbell rings on. I don't know what frequency it actually rings on. So typically when you're dealing with devices or that transmit radio signals, for example, a cell phone, if you take any cell phone and you look at the back, there's going to be some sort of FCC ID on there. I doubt you'll see it, but let me put this in your face. Now, if there's an FCC ID, at least if you're in the US, you can then look up that identifier online and find out what frequencies it transmits to. Now, in the case for Matt, I wasn't inside of his house, so I couldn't look at the device. All I could do was ring that doorbell. And then I had to either use a spectrum analyzer, which I didn't have on hand, and I also want to demonstrate how we can actually do all of this with a very inexpensive device rather than going out and buying new hardware. So the first thing is make sure you have something like this RTL-SDR, unless you already have another software-defined radio or spectrum analyzer on you. So in the US, typically when there are simple devices that transmit, it's traditionally under 1 gigahertz. If you're looking at, say, a garage, so here's my garage clicker. Again, we can look at the back and look at the FCC ID, or we can actually just scan through RTL-SDR and look for a frequency. I would start guessing around the 315 megahertz range. A lot of devices in the US will be around 315, including garage door remotes, keyless entries for a car, so that button that opens your car, even entry to the ignition for your car. So a lot of cars, you can actually just press the button and it sends a transmission to the car key, and the car key says, okay, it's okay to turn on the car. So you can see how an RTL-SDR or a similar device can actually show us a lot of really cool information. Now, I'm going to use this software called GQRX. It's free, and what it allows us to do is use the RTL-SDR to actually see the frequencies, the radio signals within certain frequencies. So I'm first going to go down to, I can actually choose my frequency here, and again, we're going to start at 315 because that's a typical band. It's actually called the unlicensed ISM band for, I believe, industrial, scientific, and medical devices, ISM. And now, right now, we don't really see much, but I'll actually do something here. I'm going to click this, which is my garage clicker. Nothing around 315. Let's just move up. Nothing. Is that something? Looks like someone's device. Oh, cool. Okay, so whenever I click this, we see something here. Around 316. So now I'm just holding it down, and we can actually see that going off. So we're around 316.5 megahertz for my garage clicker. So we can actually record this signal and then interpret it afterwards. Now, another thing I'm seeing here is that these signals, and we'll zoom in, I have to determine what type of modulation this is. Specifically, while sure, I'm sending all of this, zoom, go. Okay, cool. So we're zoomed in now. Whenever I send this garage clicker, we can see the signal. Now if I just hold it down, we see a pretty sort of solid line right here, this yellow line. What this tells me is that this is probably doing something called amplitude modulation. Amplitude modulation, AM, is essentially a way to modulate data, whether that's binary data or audio or really any kind of data. It does this by varying the amplitude of the signal. Now, if you listen to AM radio, I don't know what's wrong with you because you should be listening to SoundCloud or Pandora or something. But if you do listen to AM radio, that's actually using the same thing. That's what AM stands for, amplitude modulation. Alternatively, there could be something called frequency modulation. We don't see that here. Now what would happen is, if this were frequency modulated, we would actually see the data, or this yellow line, shifting its frequency. And something like garage door remote, which is probably just sending sort of highs and lows, we would actually, let's say we're a 316 megahertz, we might see something around 315.5 and 316.5. But we're not seeing that. We're simply seeing this long streak. So I'm going to guess it's amplitude modulated. There are also other types of modulation. There's something called phase modulation, PM, and there's a number of other types of modulation around that. But if you're familiar with AM and FM radio, those are doing the same frequency modulation and amplitude modulation. Now, let's take a look at Matt's signal. as I was going through the frequencies, I didn't find anything around 315, 316, 318, went all the way down to 300. However, as I went up, I decided, okay, well, I'll look at some European frequencies. Traditionally, we'll have the ISM band in Europe around 433, 434. So I went up to 433, 434, and lo and behold, when I hit his doorbell, I saw a signal. So let's take a look at that.
So tell me a little bit about like what you're doing.
Is this video? Mm-hmm. Oh, sweet. Okay, so whenever I ring the doorbell, we can actually see with the RTL-SDR that there's a spike around 434, 433 megahertz, which is a typical RF band in the sub-gigahertz for a bunch of applications. Usually 315 and 433, 434 are the most common. Every time you ring this doorbell, we see that spike. So it's probably around 433. So we'll get out of GQRX. We verified the frequency, which was the reason we were using that. It makes it easier to look. Now we're going to use something called RTL-FM, which demodulates radio frequency, and we're going to specify that, let's see, .433 megahertz, and we'll set it to play here. Come on. So we should hear something. So obviously there's data, and my guess from looking at it in GQRX is it's amplitude modulated rather than frequency modulated, FM versus AM. So we're guessing it's AM, so I'm going to record into Matt's door.wave. We're going to hit it once. We're going to hit it twice. We're going to wait a little bit. And then we're going to hit it a third time just to make sure we're getting the same sample each time rather than getting different samples where a system might use rolling codes and actually change the code every time. So this is probably a simple system. It's probably using the same one, but we do this to verify.
Now that we know what frequency Matt's doorbell is on, we want to record that data and demodulate it so that we can reverse engineer and understand what that signal is sending. Once we understand the signal, we can then retransmit it ourselves. So since we know it's around 433, 434 megahertz, we can use the RTL-FM program to record that. In this case, you can actually use GQRX or SDR Sharp or any other SDR software typically to record, but I prefer doing most things in the terminal when possible. And we'll actually use a script I wrote that just makes this process a little easier. But first we'll look at RTL-FM, just understand what it's capable of doing, and typically the options, I'd say the three options that are most important. For one, number one is the frequency. The frequency you use for RTL-FM is the most important thing because that tells the tuner what to tune to or what frequency to tune to. Right, frequency to tune to. There we go. Second most important is the modulation. What we want to do is we want to demodulate this. Since we looked at GQRX in the waterfall view, it looked like it was amplitude modulation. We want to change this -M to AM. So we would do something like RTL-FM. -F for our frequency, we'll say 318 megahertz, which you can just shorthand to 318M. Our modulation should be AM, not FM. And the third most important thing is the sample rate. Sample rate tells the dongle how many times per second to sample. So when we're dealing with digital data, if that digital data is getting sent faster than our sample rate, we will lose information. A default of 24K is very low. I would suggest setting your sample rate to something like 1 million. RTL-SDR dongles can probably go to 2 million, maybe even 3, depending on the dongle you have. If you have better hardware like HackRF or USRP or some other SDR hardware, you can probably get much higher. But again, we're using really inexpensive hardware that's pretty capable for what it is. And we can use this to actually just grab the binary data, or we can sort of pipe this out into a WAV file. I'm going to include a script below called RTL. This is a script I made that can use HackRF or RTL-FM, depending on whether you're using RTL-SDR or HackRF. And you can specify the modulation, which I actually default to AM in my app. And then the frequency, we'll just say the frequency is, we'll do 318 just so we can hear my garage clicker for now. So you can just say RTL 318M and go. So I'm going to click this, and we can audibly hear that demodulated data. Additionally, my program sets the sample rate reasonably high. I believe 2 million by default, so you don't have to specify that. Okay, cool. So we have that. Now again, what we would do is we would do something like this, and we would also specify a WAV file. So we'll say, you know, mat doorbell.wave, and now it will listen. It's outputting that data that we were just hearing into a WAV file, except at a different frequency at 434 megahertz. And once we have that, we can Control C, and now we have this file matdoorbell.wave. Now let's open that up and put that in Audacity. Any decent audio software will work. Now we're actually not going to use the recording we just made, but the one that I made when I was at Matt's door. So let's close this. Let's pull open Matt's door into Audacity. Audacity is free audio editing software. Makes it easy for us to view the signal. Okay, now it's not really clean. Okay. So that's Matt's doorbell if we were listening. So let's actually play this again. You can hear it. That noise right there is his doorbell. Now I pressed it 3 times. Right, there's the second time, and we can visually see over here that's the 3rd time I pressed the doorbell. Now let's look at this data a lot closer, because we want to understand what it's doing. Okay, cool. So now we're actually seeing some data, which what we have here are highs. We'll call these guys highs, and then we can call the rest low. And now what we want to do is figure out what this signal, what do we have to send to replicate this signal. Now just by eyeballing it, it actually looks like whenever we rang the doorbell, it would send a signal and then repeat it a number of times. And if we count, it looks like that's 12 times for that. Let's look at another one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Cool, so every time we ring his doorbell, it sends the signal 12 times. Now one thing we should probably do is verify that this signal is the same as this. So maybe it's just repeating, or is this entirely one signal we need to send? So what I'm going to do is, because we see these gaps, I just assume that they're repeating. They might not be, but let's find out. So what I'll do is I'll grab one of these signals at these gaps. This looks like a gap right here. I'll copy that, Control C, I'll paste it, Control V, zoom out with Command 3, and now I'll copy the beginning signal, and let's kill 2 birds with 1 stone. It's possible that this signal, each of these are the same. However, it might be possible that while these are all the same, these are all different than these. That would be called essentially a rolling code. If you have car keys and you have a button on there, typically car keys use rolling codes. The way that works is you press the car key once to, let's say, unlock, and it sends a code, sends it several times, the same code. The car hears that and says, okay, that's a correct code, I'll unlock. Now, if someone like us were listening to that code and we tried playing it later on, the car would actually disallow that code, because a rolling code says once the car hears a code, that's used and gone forever. It won't ever hear that code. The key then knows the next code to roll to. So if you press the unlock button again, it changes the code, and the car knows to also listen for that code as well. This prevents, let's say, theft of cars. However, we will probably investigate car radio frequency in a future video. Now, to see if this was a rolling code, we grabbed one guy from here, and we're going to grab another one here. Let's do that. And what we want to do is see where the... Don't paste there. Okay, cool. So now we have 2 codes from different areas, and we just want to see, do they look the same? Right? We can just eyeball it. Okay, yeah, it pretty much looks the same, right? I'm off a little bit, but that doesn't matter. These ones, or these high signals, are pretty much always high at the same time. Cool, that looks great. So it looks like Matt's doorbell is actually just this one signal. So we can probably just interpret this as 1s and 0s and then transmit it. Now, since we can look at this closer, but first, let's look at the hardware that we need to retransmit the signal. Since we know that we're dealing with 434 megahertz, let us pull open a browser window and let's look for a 434 megahertz transmitter. Now, specifically, we need a type of transmitter that's important to us. I happen to know that this should probably do what we want. Let's see here. All right, cool. 434 megahertz. $4. Awesome. Now, this doesn't necessarily mean it'll work because we need to ensure that it's doing the right type of modulation and also has the proper baud rate. We didn't talk about baud rate, but let's first look at the datasheet. The datasheet always gives information about the device you're purchasing. Okay, so modulate mode, ask, perfect. So ask is amplitude shift keying. That's exactly what we want, which is the same as amplitude modulation, but for digital data. So ask is a type of amplitude modulation. Voltage, that's the voltage we'll give it with our Arduino. And now that means we can get this device and any Arduino. So if you have sort of an Arduino or a similar microcontroller, even a Raspberry Pi, for example, would be able to control this, or a BeagleBone. Now we can take that controller and the transmitter and put them together. So let's do that. How do we actually turn this data, Matt's doorbell, into something that an Arduino can send with the RF transmitter? So let's take a look. First, let's try to understand the signal a little bit better. So really all that's happening here is we're sending some sort of identifier, and the doorbell knows to listen for this identifier, and when it hears it at this, at these highs getting sent at these specific times, then it will ring his doorbell. In the beginning, we actually see something that looks like a preamble. What this is probably doing is triggering the doorbell when it sees these four, call these signals, at this rate. It probably knows, oh, I should start listening. This way the doorbell doesn't listen incorrectly at other devices that are on the same frequency. This preamble is useful for that. So I can tell it's a preamble just because it's the same amount of time between each of these, and it just happens, one at a time. So with Audacity, we can see about how far these are apart from each other. It looks like, if we zoom in a lot, we can see it's about 700 from these numbers up here, 4.58 milliseconds, or 4.58 seconds to about 4.58, almost 4.581. So it's almost a millisecond. So it's about 700 or 800 microseconds for this signal. And if we look, we actually see all of these signals are the same exact width. This guy right here, also about 700 or 800 milliseconds. This guy right here, also about 700 or 800 milliseconds. They're all the same exact width. So what we know is we're dealing with a transmission where we're just sending these ones. There's no other type of encoding. Sometimes you'll find there's other types of encoding on top, like Manchester encoding, which would help a device listen to this signal better. I don't see anything like that. So all we need to do now is write a program that can send this data, can essentially send high for, let's call it 800 milliseconds, or I'm sorry, 800 microseconds. And then here, this is 0 for 800 microseconds, or low, high, 800 microseconds, low, high, low, high, and then low. Now this low is a different amount of time. If we just eyeball it, it looks maybe, I don't know, 5 times the length of this. This would actually be kind of annoying to This would be kind of annoying to spit out into binary. So one thing we can do instead is actually, what might be easier for me is, what I'll do is actually, I'll take a look at where all of these ones start. Since we know they're all the same length, right? Every high is the same length as the next one. So what I can do is, first, we only need to know one of these signals since they repeat. So let's actually cut all of this stuff out. Let's get really close. We don't need anything else. So we can delete most of this stuff. that. Zoom in, delete. You only need the first signal. Delete that. Zoom in, delete this. Okay, cool. So now our very first one, our very first high starts at 0. So let us open a new script. We're going to create on the Mac doorbell.c. This is really just an Arduino script. Ring Matt's doorbell. That'll go away. Now in an Arduino program, I'll include the source as well. You always have a setup and loop section. With our Arduino, I'm using Arduino Nano, as you can see here. And with this RF transmitter, with this guy right here, we actually have 4 pins. And let's actually take a look at the datasheet and see what those pins are. Okay, so we have 1 ground. So number 1, this pin right here, we're going to tie to our ground on our Arduino. 2, data in. So this we just tie to a data pin on our Arduino. Doesn't matter what, we'll probably just tie it to pin 9. 3, VCC. This is our voltage. So we need to understand what kind of voltage we need to send to this guy. Should be specified up here. Supply voltage anywhere from 1.5 to 12 volts. So pretty much any Arduino should work using a 3.3 volt Arduino or a 5 volt Arduino. You should be good as long as you just tie your voltage out from the Arduino to the device. And then an antenna. We don't need an antenna. This should suffice. Cool. So let's first set up our pin. Let's say pin 9. No, on mine, yeah, I'm using pin 9 to connect between the Arduino and the RF chip. So we'll call it RTX pin 9. You can call this anything. Let's say pin mode, TX pin, output. This says we are going to use that pin on the Arduino, pin 9, as an output, where we'll actually be sending data, highs and lows. Now our loop function, let's not worry about that. Let's actually just create a ring doorbell function. Now what we want to do is we want to take these, and here we want to send a high for 800 microseconds. So what we could do is we could do digital write TX pin high, and then we can delay 800 microseconds. Okay, cool. Then we could basically keep doing this for all of these, but that would be a pain. So instead, right, then what we would say is digital write TX pin low, delay 800, right? That would be then low for this amount of time. Then we do high again, then low. It would become complex around here because we need to count all that. So what I'm going to do instead is I'm going to make an array of where all these ones or highs start. So this one starts at 0. So let's make an array. These are floats. Let's do the top here. Start. I don't know how many. We'll just say 30. And 0.0 is where the first one starts. This is about 0.0015, 0.015. We could be a little more specific if we wanted. The next one is 0.03, 0.003. Okay, so here's where all the ones are. So if we were to zoom into this last one, this should be around 0.08, which we see, yep, 0.08, about 0.083. These don't need to be perfect, especially with a simple device like this. Now what we're going to do, instead of ringing the doorbell, we're going to create a loop, and we're going to say, all right, first off, this is not 30 values. I believe this is 22. Right, 1, 2, 3, 4, all the way, plus 1. Now we'll actually loop through this. Okay, so what we want to do is we want to, actually, let's go back. Let's make this a define. So we want to be high for, we'll call it a bit period. I don't know what you'd really call this, but define bit period. We'll call it 800. So we turn this pin high, which would then create this type of signal for 800 microseconds. Now, I don't know. Now, what I want to do then is I just want to wait until the next one. So I will then take us low. We don't necessarily know when the next one will be. So what we will do is, okay, so we're done with the code here. I won't go through it all here, but you can check out the website below where I'll go over some of this. Also, you can check out the GitHub where all of the code resides on. You can see ultimately how we ring the doorbell by bit banging, essentially sending the transmitter when we want to go high, when we want to go low. And we also have code using the FONA so that we can receive SMSs. And when the SMS has a specific word, when it has the word doorbell in it, then we actually ring the doorbell. We run the transmitter. You will need to use my version of the FONA library. That's the Adafruit FONA library. That's also on my GitHub. And the reason is I added a feature that allows the FONA to send an interrupt whenever it receives a text message. By default, this only sends an interrupt on the RI, or ring interrupt pin, when a call is coming in. But I didn't want to keep polling the device whenever to see are there new messages. Instead, I have this send an interrupt to us, and then we know to check for new messages. And seems like the right way to check for new messages. Anyway, that's it for now. I have more details on radio frequency, RTL-SDR, reverse engineering, and other things on the website that I have included. And I hope you enjoyed this. Thanks. Bye. Also, here is the basic schematic. You can find this on the website, so I highly suggest going to the website. You'll see the schematic, you'll see all sorts of other information. There's some more information on modulation schemes and radio frequency, how this FONA board works, the requirements for it, the type of SIM card you need, power, and links to everything you could need in this whole thing. I mean, you can pretty much, if you don't need the GSM board, right? You could just sort of build something that replays, and you could do all of that with RTL-SDR, Arduino, RF transmitter. Combined, it's going to be less than $30, and all of these are reusable. So it's a pretty powerful pack for just for that much money. You can do a lot with it. So check out the website, and also if you want to see more videos really long like this that I go rambling on for half an hour, hit subscribe. All right, thanks. Bye.